In section 6.1, well, chapter 6 really, we explore a continuous probability distribution. The distribution is called the normal distribution, and that's for random variables that are continuous. So now you're thinking about things like the price that you might pay for a car, or the amount of time you spend on hold when you call a call center for support. Those things we can make into a grouped frequency distribution, so we have a histogram that is grouped maybe. So let's say we're talking about the amount of time you spend on hold, and we're grouping this in 0 to 1 minute, 1 to 2 minutes, 2 to 3 minutes, 3 to 4, 4 to 5, 5 to 6, 6 to 7 minutes spent on hold. But since this variable is continuous, we could theoretically chop up all the intervals into smaller class widths. Right now our class width is 1, but we could make the class width a half, we can make the class width a fourth or a third, and we'll start to see that these little bars become closer and closer to what we call a continuous function. And from chapter 2, when we describe shapes of distributions, you can see that this one is normal, or it's bell-shaped or symmetric. And so that's what we'll be studying in this chapter, compared to chapter 5, where everything was discrete. So you had 1 car in your driveway, or 2 cars in your driveway, or 3 cars in your driveway. Now we have a continuous distribution. And the probabilities for those are defined by this thing called the normal probability density function, because now we don't really want to talk about the probability of waiting on hold for exactly 3 minutes, because that's just one case, but maybe between 3 and 4 minutes. So we want to know what the probability density is for that range of a continuous variable. The function is a little scary. It is 1 over sigma times the square root of 2 pi times e, Euler's number, to the negative x value minus the population mean squared divided by the population variance times 2. It's kind of a freaky function. Hopefully you recognize a few things, like pi is pi, 3.1415, yada yada, right? Non-terminating, non-repeating decimal, just like e, Euler's number, 2.71828, yada yada yada. So those are constants, although they look like variables. But what we have of note are that this function really depends on just 2 things we call parameters: the standard deviation of the distribution and the mean of the distribution. Those are parameters. Mu and sigma, which are population mean and population standard deviation. So any normally distributed variable has a probability density function related to it that depends on the parameters that are the mean and the standard deviation of that population. Then the variable would be x, so that's where you would say between 3 and 4 minutes. We could put in the values of that to find the probability density function at that particular point, or on a range of intervals. Now, before we get too deep into that thing, let's talk about some properties of normally distributed random variables, or a normal probability distribution. The first thing you'll notice is that it is symmetric. It's symmetric across the mean. Not only is it symmetric, but it is bell-shaped. So it has 1 peak at the mean, which also will be the median, and also the mode. So all measures of central tendency converge at this 1 peak. There is a horizontal asymptote. On the x-axis, so that's the line y equals 0. For any normally distributed variable, like we had caller ID wait or caller wait times up here, we would not see any values or frequencies below 0. We might see a frequency of 0, that no one waited less than 0 minutes, because that's not possible, or no one waited more than 11 minutes, or what have you. So there's some horizontal asymptote where we can't get below that. No one would weight negative, right? There wouldn't be negative people weighting minutes, so that's a pretty natural extension there. Another property is that there are inflection points. Inflection points are changes in concavity of the curve. If you look at a normally distributed variable, we have places where it's concave up here, like where it might hold water if you put water in it, and then we have other places where it's concave down, like that. These inflection points happen one standard deviation away from the mean. So we might say that one standard deviation from the mean. That helps us when we're making the curve. And then the last property, the most important property for us, is that the area under the curve, the entire curve, is 1. Because we're talking about possibilities, possible outcomes of some random variable experiment like waiting on hold. And so if we were to talk about the probability of waiting on hold between 0 minutes and infinity minutes, then that probability would be 1. If we talk about the frequency, somewhere you would be on that curve. An important connection for this whole chapter is that area under the curve is the same thing as probability, or can be used to describe probability, because remember, the curve is the probability density function. How likely are we to see that result? So the area, or the probability of the whole situation, is always 1. We'll use that a little bit more later, but first let's investigate properties of this curve and how they are defined by the mean and the standard deviation for the population. So I've drawn two red curves here, two normal distributions. They both have a mean of 0 and a standard deviation of 1, and you'll see that noted in the red letters there. Mean 0, standard deviation 1. If, however, we were going to take this same distribution and change a parameter. So now I've drawn a blue curve, matches exactly the red curve, but now I would like the mean to be 3. What that does is simply shift the curve up the x-axis until the single peak is now at 3. The standard deviation is still 1. You'll notice that the inflection points now occur 1 distance from the mean. So we have an inflection point at 2 and we have an inflection point at 4. That inflection point measures the spread of the distribution, and that is the same as it was in the initial case, in the red case. If we look at the next curve though, this guy's taller, so not very exciting to us. However, if we would like to draw a new curve where the mean is still 0, so now my single peak will still be at 0, but I would like to change the standard deviation from 1 to 2. So now I'm changing the spread of the distribution. The inflection point is no longer at 1 away from 0, but now it's at 2 away from 0. So I can draw a new curve, single peak at the mean, inflection points at 2 and -2, and you'll see that what happened basically is the red curve got squished down into the green curve because the green curve got spread out. So we still have the same probability, or that same area of 1 underneath the curve, but now we're changing the shape of the distribution by messing with the parameter, the standard deviation. So here in this case, just notice the effect of the mean and the standard deviation on the distribution. Remember that that can be specific to any case. We could have a mean of 19, we could have a standard deviation of 32. It will simply change where the curve is located on the x-axis and the spread of the curve. If we have a distribution that's approximately bell-shaped or roughly normally distributed, then we can make a conclusion about the amount of data included between standard deviations. So remember, if it's a bell-shaped distribution, the mean is right there in the middle. the first standard deviation is 1, or the first hash mark, the inflection points are 1 standard deviation from the mean. And between those 2 points, we capture 68% of the data values. So I'm going to show you the empirical rule 2 ways. One way just on this table, and then one way in bullet points. So the first bullet point would say that 68% of the data values from this distribution lie within 1 standard deviation of the mean. If we go 2 standard deviations from the mean, so we're 1 standard deviation from the mean now, but let's go 2 standard deviations, so 1 more standard deviation from where we were. Now we've captured 95% of the data values. So in words, 95% of the data from this distribution lie within 2 standard deviations of the mean. And if we go 1 more standard deviation from that, so we are at 3 standard deviations from the mean, now we have captured 99.7% of the data values. So almost 100% of the data values lie within 3 standard deviations of the mean. That helps us understand the curve. We can make predictions about values based on this information. We'll narrow this information down in coming sections where we can be a lot more exact about the percentage of values we expect to see in a particular area. But first, this is like a nice little summary of what's going on with the curve that we can use to answer questions. One of those questions might be this. We have an SAT distribution. It's bell-shaped, so it looks a curve like this with a mean of 515. So that mean needs to be in the middle of the curve. The standard deviation is 114. So we can complete the curve by adding 114 to 515 to get 629 for the first standard deviation from the mean. And we can take 114 away to get 401. So within 1 standard deviation of the mean, which we've now drawn, we can talk about the percentage of scores between that. Between 401 and 629, we would expect to see 68% of the data values because of the empirical rule. We're within 1 standard deviation of the mean. But what if we go further? Let's just complete the curve. If we go another 114 after 629, that gives us 743. And another 114 beyond 743 is 857. Or we can go backwards. So let's finish this direction. 401 minus 114 is 287. And 114 back from that is 173. So now we've completed the curve, just so we can kind of interpret the coming questions. What's the probability that some scores are 401, less than 401, that's this area of the curve, or greater than 629, this area of the curve? Well, we remember that everything under the curve was a total of 1, and we do not want the area in the middle, right? 68's right in the middle. That's not the area we want. Now we want the green area, the area on the outside of 68%, so we'll subtract the 68% and arrive at the green area, which is 32%. So 32% of the data lie on the outside. Now, because you remember that this curve is symmetric, we can also use symmetry. If there's 32% in these green tails, I could say that I know that there is half of 32. So that's 16% in each tail. 16% here, 16% there, should I want to answer that question. The next question is, what percentage of scores is greater than 743? That's not 1 standard deviation away, but it is only one side of the curve. So let's see if we can find that probability. knowing what we know, if we are 743 is 2 standard deviations from the mean. So from the empirical rule, we knew that 95% of the data was here between 287 and 743. So the leftover parts, the parts that are not between those 2 standard deviations, are 1 minus this 95%, which is 5%. That 5% needs to be split up into the 2 tails. So here's one and here's another tail. So 5% divided by 2, that's 2.5% on the left and 2.5% on the right, which is what we wanted to find. So the answer, the percentage of SAT scores greater than 743, is 2.5%. And that should be enough to get you started on 6.1. Let me know, of course, if you have any questions.